Okay, good morning. The next topic we are going to discuss today is a signal flow graph. Okay, what is meant by signal flow graph? Signal flow graph. So the name itself it told you that the signals which is flowing in a control system can be represented graphically. Okay, so a flow graph is nothing but a graphical representation of a control system. So we can represent the control system in a subsequent blocks. So that blocks can be removed and it can be represented by the signals from one node to the another node, and we can easily represent the system in a signal flow graph rather than we are um, writing the blocks, many blocks in the control system, which will be a very complex and which will be confusing to the many one in the industry as well as for the academic purpose. Okay, so the block diagram representation of the system can be converted into the a graphical representation of the control system, which is called as a signal flow graph. Okay, so the signal flow graph is nothing but we are having some the basic terms which is present in the signal flow graph. Okay, so each and every point is represented by a node. Okay, what is mean by node is from the one point to the another block we are transferring the signal. So each and every point, the input is one node, the output is another node. Likewise, it will be transferring to one node to the another node. Okay, and you are having the branch. Okay, what is mean by branches? So the branches which is connecting the two nodes is called as a branch. Okay, so we already you may know about in a first years uh, while you are discussing about the BEEE, the this basic things can be taught to you. Okay, the branch is a point where connecting the two nodes, which is a branch. Okay, and so this is a two important thing. Then you are having the feedback. Again, the feedback signal is in the same way it is represented in a block diagram reduction. Okay, so uh, for example, we are to where I'm going to draw some signal flow graph from 1, 2, 3, 4, 5. So we can write the nodes as 1, 2, 3, 4, 5, and I'm representing the transfer function of the block in a branch. Okay, so every branch is a block diagram or the transfer function. So if the transfer function is 1, you can write it 1. If it is some g1 or g2 or g3, okay, and input is given here, so it is always the input is represented in R and output is represented as C. Okay, so this is a simple representation of a diagram. Okay, so the original block diagram, you are having the three blocks G1, G2, G3 will be connected in series. Okay, that will be represented as a this signal flow graph. So if you see that the original system is G1 to G2 to G3, and this is your output and this is your input. So this system is converted into the signal flow graph. Okay, so the blocks can be removed and we are only drawing the nodes, and on the nodes the branches we are representing the what is the value of that particular transfer function will be represented here. So if there is any feedback, then again it will be given to us the feedback from 2 to 4. This is maybe minus h1 or minus h2, like that it will be represented. Okay, if there is a no transfer function for the feedback, we can represent it as minus 1. Okay, minus 1 represents it is a negative feedback. If it is a plus, it is a positive feedback. Okay, so this is the way you can um, represent a signal flow graph of any control system. Okay, so first we are will discuss about the how to uh, reduce the your signal flow graph into the final transfer function. So this for a simple system I am represented as simple flow graph. If it is a complex system, the signal flow graph is again a complex one. Okay, so we have to reduce it into some transfer function. So how we are going to reduce it into the transfer function is by using the signal flow graph reduction. Okay, so the signal flow graph reduction is the technique which is used to convert the overall the signal flow graph into the a single transfer function. Okay, so by using the Mason's gain formula, we can able to convert the Mason's as given a formula to calculating the transfer function from the signal flow graph. So before that, we can discuss about some basic rules for converting a signal flow graph into the transfer function. Okay, the first one, so if you are having the two nodes and it will be connected to the another node, so that is 1 2 3, so it is A, it is B, then here what is the equation is, it is A plus B. Okay, so this is a summation. If it is in a series, so here the node 1 2 3, so here the transfer function is A, here the transfer function is B. What is the output is? So the output is AB. It is in a series. Okay, in a series is multiplication. If it is in a parallel, it is a addition. So like in a block diagram reduction technique. Okay, so next one, so you may have the combinations of series and parallel. Okay, so you may have like that 1 2 3 and 4 nodes. Okay, this is A, B and this is C. So you will get A plus B into C. So the output is the combination of series and parallel. So A plus B into C. So we can get the any things. So again the feedback. So how we are reducing the feedback is, so from one node to another node, again we are giving back the feedback with help of -1. Okay, and this is a node 1, node 2, and here it is the transfer function is G, and if you take the feedback is -h represents the negative feedback and +h represents the positive feedback. So if it is a negative feedback, again the like the formula we discussed in the block diagram reduction, the same formula will be used for a closed loop transfer function. So GCL equal to G divided by 1 plus GH. Okay, if it is a positive feedback, so in the same way the positive feedback, the feedback is plus H, okay, or plus 1, anything. Okay, so 1 2, here the transfer function is G. So the closed loop transfer function or the reduction of this one is G divided by 1 minus GH. Okay, so this is the basic rules which is needed to reduce your signal flow graph into a transfer function. So for reducing this, the Masons have given you the formula. This is called as a Mason's gain formula. Mason's gain formula. Okay, the Mason's gain formula is to deriving the transfer function of any system. Okay, so the transfer function is nothing but 1 by del so 1 by del into summation of k into pk into del k. Okay, this is a Mason's gain formula. So where del is having the separate equation and pk is here, the k represents number of forward path. Okay, the k represents number of forward path. Okay, it may be 1 2 3 4 or any number of forward path can be present in the signal flow graph. And the pk, okay, so next we can discuss about what is mean by pk is. Pk is nothing but the gain of the forward path, each and every forward path. P1 is the gain of first forward path, P2 is gain of second forward path, like this. Okay, so it is the gain of or gain product of kth forward path. Okay, and what is del k is? The del k is nothing but it is the value of del is calculated, or the value of del calculated for not touching that particular kth forward path. Okay, if there is no nothing is present, we can represent the del k. Okay, so the del k equal to 1 if there is no component or nothing is present in the loop. Okay, for the particular power path. Okay, so this is what is del. So here the important is how to calculate the del. Okay, the del equal to, okay, it is 1 minus sum of individual loops plus sum of two non-touching loops and alternative sign again minus sum of three non-touching loops plus and so on. So it will be go on to the one individual loops, two non-touching, three non-touching loops, four non-touching loops, and so on, which is present in the signal flow graph. If the complexity of the signal flow graph is higher, you may have these two non-touching, three non-touching, and four non-touching loops can be present. Okay, so we can reduce the signal flow graph with help of this Mason's gain formula by calculating the del and pk and del k for every forward path, and we can easily derive the transfer function of that particular signal flow graph. Okay, so mostly the g of s equal to, it is nothing but the output is c of s, input is r of s. Okay, so c of s by r of s nothing but this equation. Okay, so we can discuss with one example for deriving the transfer function by using the Mason's gain formula. Okay, so we are going to reduce this